Everyone, welcome back to Fractal Frontier Maths. In the previous video, we discussed the Picard-Lindelof theorem, a fundamental result that guarantees existence and uniqueness of solutions when the function f of xy satisfies the Lipschitz condition with respect to y. If you haven't watched that video yet, I strongly recommend it. The link is in the description below. It will help you clearly understand how today's example connects with that theory. We will look at a problem from the CSIR NET Mathematics December 2014 paper, which illustrates how the Lipschitz condition guarantees uniqueness and restricts the behavior of the solution curve. So the problem is given that y is a differentiable function and satisfy the differential equation dy over dx equal to function of y for all x belongs to the real number r. The initial and boundary condition are y0 equal to 0 and y1 equal to 0, where f is given as a r to r Lipschitz continuous function. Then we have to test which of the following options is or are correct. In this video, we have explained the Picard-Lindelof theorem, which is also called the existence uniqueness theorem, which states that if a function f of xy defined on a domain D of R cross R is continuous with respect to variable x and Lipschitz continuous with respect to variable y, then the initial value problem dy over dx equal to function of xy with the initial condition yx0 equal to y0 has a unique solution in an interval containing x. In the given problem, f of xy is simply function of y, which is a Lipschitz continuous function. F xy equal to fy is a Lipschitz continuous function. So, by Picard-Lindelof's theorem, the given initial value problem, which is dy over dx equal to fi subject to the condition y0 is equal to 0, has a unique solution. Since we are given that y0 equal to y1 equal to 0, so by Rolle's theorem, where exists c belongs to 0 1 such that y dash c is equal to 0. Now, from the given initial value problem, y dash x is equal to function of y at x equal to c, y dash c is equal to function of y of that is f of yc is equal to 0. Okay. Now we will assume that the function zx equal to y star, which is equal to y at c, is a constant function. Its derivative with respect to x is 0 and function of z x, that is f of y star, or we can say f of yc, which is equal to 0. Therefore, zx is a solution to the ordinary differential equation dy upon dx equal to function of y. But the solution is unique, therefore zx must be equal to y, that is y of c must be equal to y of x. Since y of 0 equal to 0 and y of 1 equal to 0, therefore y of c is equal to 0. Okay. And hence the solution of the given initial value problem is identically 0. So yx is identically 0, which means yx equal to 0 for all values of x. Now we will analyze each option one by one. The first option is yx equal to 0 if and only if x equal to either 0 or x equal to 1, which is not true because yx is anywhere 0. It is identically 0, so this option is incorrect option. Second one is y is bounded. Since yx equal to 0 is a constant function, therefore y of x is bounded. So it is a correct option. Now the option 1 is saying that y is strictly increasing, which is incorrect because y of x is 0 is a monotonic increasing function, not strictly increasing function. Option number 4 is dy over dx. Since x is equal to 0 everywhere, so its derivative with respect to x is also 0, is bounded. So the option is dy over dx is unbounded is not correct. Thus, the only correct option is option number 2. Okay, this was the CSIR NET Mathematics December 2014 problem showing how the Lipschitz condition ensure uniqueness. If you haven't watched the earlier video on Picard-Lindelof's theorem, check the link in the description. If you found this helpful, please like, share and subscribe to Fractal Frontier Math.